Here in this first part of our first module, Introduction to Biomechanics, I'm going to provide an overview of how biomechanics fits the analysis of human movement and behavior, and then we'll follow that up with some basic foundational definitions in this field of study. And so if we start with examining two different athletes who are at the very top of their respective sports, and when we think about how these two athletes operate, there are some similarities and some real differences between the two. And I like to use the analogy of two different cars. So on the left-hand side, here we see an athlete and a car that is designed for maximal land speed movement. On the right-hand side, here we see an athlete and a car that are designed for lower land speed movement, but very long duration, very efficient type of operation. And so either way, whether we're talking about the athlete and car on the left, the athlete and car on the right, to carry out their functions, we're basically talking about the generation of mechanical energy, which raises the question of whether this system is designed around the generation of maximal power and speed, or designed for long duration and durability. The one common feature between, really all of these systems, is that they're electrically or command controlled. The driver in the vehicles represent the command controller, while the central nervous system represents that command controller using electrical energy as well as chemical energy for their functions. The one other feature that's common to all four of these photos is that in order to carry out the generation of mechanical energy, fuel combustion is necessary. Now, unlike the vehicles here on the left and right hand side, which can only use one type of fuel, as humans, we have the option of selecting from a range of different fuels to drive that mechanical energy. Specific to these vehicles, on the right hand side, here we see this one car on average is rated at has an efficiency rating of 28 miles per gallon, while the vehicle on the left is rated only at 14 miles per gallon. So here we see a much lower efficient vehicle, but we go back to understanding that this vehicle is designed for maximal land speed, and efficiency is not a primary determinant in its design. Much like the athlete in this particular scenario, this athlete is a sprinter, and the goal of this sprinter is to achieve a maximal land speed over a very short distance, as compared to the athlete on the right, which is who has trained to achieve a lower land speed, but able to hold that lower land speed for a very long period of time. But to understand the elite athlete, or just the ability to carry out activities on a daily basis, and what factors consider into the ability to carry out those tasks, anatomy is certainly the first item we should be thinking about. So the structural characteristics and the body type, at least when it comes to elite sports, will have a considerable weighting on how well that athlete performs. When we talk about the neuroscience of human activity, we think about the central nervous system. More specifically, we talk about muscle activation and control, and this latter item we will touch on a little bit later on in the course. We have to also consider that the metabolic characteristics, which is going to be a reflection of muscle fiber type, will differentiate this athlete from, say, a marathon runner. We will not be spending a great deal of time identifying metabolic characteristics in humans. This course is focused on biomechanics. But I just want to add in one more point here, that the nutritional profile of these athletes, the nutritional profile of the human organism is important to consider, because the ingested amount and type of carbohydrates, lipids, and proteins will dictate what kind of fuels are available to the motors of human movement, and those are the muscles. So let's pivot back over to biomechanics, and we're going to define biomechanics simply as the mechanics of biological systems. And in this course, we're going to focus for the most part on the human organism and the whole person as the biological system. Keep in mind that when we talk about biomechanics and biological systems, we could be referring to the heart, we could be referring to a single muscle cell in that muscle, or a single protein in that muscle cell. And we'll take a look at some examples where we'll identify a single muscle protein and its mechanical behavior. A very large field of study in the field of biomechanics relates to the mechanics of plants. Although we won't be focusing on that in this course, it is certainly something to keep in mind in the future. So what we've talked about so far are different examples of biological systems, living things. But when we talk about mechanics, we're going to apply that field of science that describes and predicts the conditions of rest or motion. These are two very important terms that we'll focus on separately in the first half of this course, of bodies under the action of forces. And so we're going to talk about rest or motion, two separate conditions, simultaneously with the action of what we call forces. So this slide here, I think, nicely summarizes the two major branches of biomechanics. So when you think biomechanics, the first thing that I would recommend and that should come to mind are two words: motion and forces. So we'll start on the left-hand side. When we talk about motion, this refers to the mechanical behavior of any given biological system as we defined it on slide number 4. And so some examples of mechanical behavior, as we saw in some of the early examples in this lecture, how fast or how much a person is moving. When we think about the heart, we know that blood accelerates out of the left ventricle during the systolic phase of the cardiac cycle, which is the contraction phase of the cardiac cycle. And using ultrasound imaging technology, we can actually observe that blood moving very, very quickly out of the left ventricle soon after it starts contracting. 90% of ankle injuries occur as a result of what's called an inversion movement, where the foot moves towards the midline of the body. And when that occurs, ankle ligaments that are designed to provide stability stretch beyond their normal length and will stretch at different rates. And so the magnitude of the stretch, how fast that stretch occurs, will dictate the type and magnitude of the injury to the ankle. The important point to think about when we think about motion and mechanical behavior, these are observable things. And so being observable, we can measure them directly. Please keep in mind that when we talk about changes in the shape of biological tissues or structures, we're going to quantify that as motion as well. This general branch of biomechanics is simply referred to as kinematics. This contrasts with the right side of the slide, which are forces. And when we think about forces refers to the thing that governs this mechanical behavior on the left-hand side. So one example, and we'll only use one example in this instance, when we ask the question, how much force, muscle force, is generated by the low back or thigh muscles to stand up from a chair? We know that in order to stand up, we have to activate those muscles, but the question here is how much force must those muscles generate? We can gain estimates of what those forces are, but they're not observable. what we actually observe in this example on the right-hand side is the person actually moving from a seated to a standing position. However, we can indirectly get a sense of those biomechanical forces by observing the changes in mechanical behavior and applying biomechanical modeling techniques. So we can perform a series of calculations to give us a very good estimate of what those forces are, although we don't have direct measurements of those forces. And that falls under the general branch called kinetics. So one easy way to remember the difference between kinematics and kinetics is the letter M. So M for motion. When you think kinematics, think mechanical behavior. So when we talk about motion, motion refers to the physical location of an object in space, and we'll define space in a separate lecture as a function of time. Time has to be on our x-axis when we start to think about motion and the kinematic variables. And the key variables we will focus on in this course is position. You can't figure out velocity without knowing where an object is with respect to some frame of reference, as well as acceleration. So these are the three kinematic variables that will be the focus of this course. There are three types of motion. There's what we call linear motion, which is further defined as either rectilinear or curvilinear. There's angular motion, which refers to the rotation of an object about a point or an axis. And there's the combination of the two, which is referred to as general motion. And so we'll take a closer look in a little bit more detail of these different types of motion in the kinematics unit of the course. Now, going to the right-hand side of our previous slide and talking about force, a very common definition for force that you'll encounter in various physics textbooks, for example, is that force is defined as a push or a pull. And it's defined as a push or a pull because force is actually a very difficult thing to define. But we will give it a shot here. But we're going to define force as an action, this thing that causes an important inclusion here, or it tends to cause. It attempts to cause an object to change its state of rest or uniform motion in a straight line. So some examples of forces that we will spend some time focusing on in this course include muscles, ligaments. When ligaments stretch, they resist stretch by exerting forces, and we'll talk about gravity as well. But we'll spend just a moment here to define what are considered the four fundamental forces of the universe. The one force that will factor into our biomechanical modeling approaches is gravity. And so when I talk about gravity, I'm making very specific reference to Newton's law of universal gravitation. The second force that is a fundamental force is the electromagnetic or weak force, which is basically electron-electron repulsion between molecules or atoms. And that is the majority of forces that we typically think about when it comes to muscle forces, ligament forces, ground reaction forces. They're all generated through electron-electron repulsion at the most fundamental level. The two other forces that we will not be focusing on, or we won't address at all in this course, but they're nevertheless very interesting, is what's called the strong nuclear force. This is the force holding nucleons together in the nucleus of the atom, and the weak nuclear force, which is responsible for what we call radioactive decay. And so we'll conclude this first part of the introductory unit by introducing three subdivisions of biomechanics, which we'll examine in a little bit more detail in part 2 of this introductory module. So the first division that we'll address is where we'll spend most of our time in this course, and that's the biomechanics of rigid bodies. The last unit of this course will take a more detailed examination of deformable bodies or deformable solids, and those are objects that can change shape, that do change shape under the branch of tissue mechanics, and we'll address that later on in the course. And then the third division of biomechanics, or rather subdivision of biomechanics, that unfortunately we will not be focusing on in this course, but in the subsequent parts of this introductory module we will take a look at some examples, is fluid mechanics. So this ends the first part of our introductory module on the introduction to biomechanics.